everyone, my name is Miriam Adele and I'm a third year BME student, and today I'm going to be doing a homework problem from ECE3320, which is Introduction to Circuits, and I believe it's the same as ECE3330, it's just a different course number. The homework problem that we're going to be looking at today has to do with Thevenin equivalent circuit. What a Thevenin equivalent circuit is, basically when you are given two open terminals like this, whatever is going on to the left or the right, in this case it's to the left, of the terminals, like this circuit right here, whatever's going on here, no matter how many sources or resistors, all of this can be simplified to one voltage source and one resistor. And so the voltage source is called the Thevenin voltage, which is also referred to as the open circuit voltage, and the resistance is called the Thevenin resistor. This resistor right here is the Thevenin resistor. And the way you find the Thevenin resistor, like the formula for it, we know that resistor equals the resistance is equal to the voltage divided by the current. In this case, it's the same thing. It's equal to the Thevenin voltage divided by the short circuit current. Now, you might ask yourself, what is a short circuit current? What a short circuit current basically is, it just means that we have to short circuit it right here and find the current that's flowing through the short circuit, like this. But we'll get to that later. Now, what an open voltage is, it's basically this voltage right here. It's the voltage drop between those two terminals. Even though it's it's an open circuit, there's still like a potential for energy, so there's still going to be a voltage drop between these two terminals. Now, there are many ways to find the Thevenin equivalent circuit, and I'm going to show you two methods in this video. So basically what you're trying to find is your Thevenin voltage and your Thevenin resistor, so that you can form this circuit right here, which is the Thevenin equivalent circuit. Now, let's start with the Thevenin voltage, which is this right here. How can we find this? Now, if you look at this 8 ohm resistor right here, you see that it's connected to an open circuit. So basically, there's no current flowing through this resistor right here, meaning there is no voltage drop. So this resistor, in this case, we can actually ignore, because it's not participating in this voltage drop. There's no current going through it. So now that we're going to pretend that we don't have this resistor for now, finding the Thevenin voltage is hopefully clearer to you now, because we have a source voltage and then we have two resistors in series. So basically what we're going to do is use the voltage divider formula, which is the current source multiplied by the 40 ohm resistor, because as you can see, this voltage drop right here is essentially the same as the voltage drop across this 40 ohm resistor. So it's going to be the 40 ohm resistor divided by 40 plus 10 ohms. We get negative 12 volts. Now that is your Thevenin voltage. We're going to hold on to that. Now we need to find the Thevenin resistor, which again, it is equal to the Thevenin voltage divided by the short circuit current. Now, how can we find the short circuit current? Basically, again, we're going to short circuit this circuit right here, and we're gonna try to find this current. Now, how do we find this current? There are many ways in which you can find this current. I'm going to use the mesh method. So here I have mesh 1, here I have mesh 2. So at mesh 1, we have 15 volts plus 10 times I1 plus 40 times I2 minus I1. equals 0, and I'm going to simplify this. I'm going to end up with 50I1 minus 40I2 equals to negative 15. That is going to be my first equation. And at mesh 2, we are going to have 40 times I2 minus I1 plus 8 times I2 equals... Okay, so that's going to equal to 0, and I'm going to simplify it. So we will have negative 40I1 plus 40I2 plus 8 I2 equals 0, and this can be further simplified to negative 40I1 plus 48I2 equals 0. That's my second equation. And let's just free up some space here. Okay. So now what I'm going to do is I'm going to solve for I2. You can solve for I1 as well, but in this case we're trying to find I2 because I2 is in this second loop where this short circuit is, and also this short circuit current is going to be flowing through this 8 ohm resistor. So that is what we're actually most concerned with. So I'm only going to solve for I2 because that's the current that I need at the moment, but feel free to solve for I1 as well, just for extra practice. So I'm gonna take this equation right here, and so it's going to be 40I1 equals 48I2. So I1 is 1.2 I2, and I'm going to substitute this back into equation 1, which will give me it'll give me 50 times 1.2 I2 minus 40 I2 equals negative 15. And when you simplify this, you get 60 I2 minus 40 I2 equals negative 15, which means that it's 20 I2 equals negative 15. So I2 is going to be negative 0.75 amps. And that is your short circuit current. And it's negative because it's pointing, that means that it's pointing down, which you already assumed right here. So now, we have the short circuit current. We need to find the Thevenin resistor. Okay, so we're gonna do that down here. So it's equal to the Thevenin voltage, which we already found to be 12 volts, over short circuit current, which is going to give us, let's see, 16 ohms. Now we're all ready to construct our Thevenin circuit. And we're basically going to have the same terminals in the original question. Sorry. And we're going to have a voltage source of 12 volts and a Thevenin resistance of 16 ohms. Alright, now I'm going to show you another method which I find to be a little bit simpler and less time consuming to find the Thevenin circuit. So what a Thevenin circuit or a Thevenin equivalent circuit basically is, again, it's just a simplified circuit of whatever is on the other side of the terminals, right? So another way in which you could do this is by using transformations. So I'm going to start using transformations starting from the left side of the circuit until I reach the terminals. Again, we have the voltage right here. Until I reach the terminals. And whatever voltage source and resistor that I've simplified this portion of the circuit to is going to be my Thevenin equivalent circuit. And you're going to see that we're going to get the exact same result as this circuit right here. So I'm going to start simplifying with transformations by looking at these two. We have a voltage source and a resistor in series, so we can simplify that to a current source with that resistor in parallel. So again, since we have a voltage source right here in series with the resistor, we can transform this to a current source in parallel with that same resistor. Now, the current source is going to be I equals V over R. So that is going to be negative 15 volts over 10 ohms, which will give us negative 1.5 amps. So I'm going to redraw that circuit. And I'm going to add the same resistors that we had in the original one. So we have the 8 ohms and the 40 ohms. And then I'm gonna bring down the 10 ohm resistor here. And I'm gonna add the the current source here. And it's going to be pointing down because it's negative. And it is 1.5 amps. Okay? Now, if you look at the circuit, how can we simplify it even further? Sorry, this is 40 right here. 40. Okay. If you look at these two resistors right here, you can see that they are in parallel. So how can we find the equivalent resistance between these two? So it's going to be, the product over the sum. So if we do 10 times 40 ohms over 10 plus 40, that will give us 8 ohms. Okay, so I'm going to redraw this circuit again. To its simplified form. We're going to add the same current source here. Now here we have 8 ohms, and here we have 8 ohms. Now what I'm going to do next is, if you look at the circuit, again, you have the 1.5 amps current source and a resistor, and they are in parallel. So that means that you can transform them to a voltage source in series with that same resistor. So the voltage source is going to be I times R. So that is, and this isn't, well, no, because it's already pointing down. Okay, it's going to be negative 1.5 amps times 8 ohms. That will give me a voltage of negative 12 volts. Now I'm gonna redraw, and this should ring a bell. We saw this somewhere else. Anyways, we'll get back to this. Now I'm gonna redraw this circuit, and I'm gonna have the voltage source right here of 12 volts, and I'm gonna bring this resistor up here, and we have the 8 ohm resistor here as well, and our two terminals. Now we can simplify this even further. These two are in series, so it's going to be 8 plus 8 ohms. And I'm going to redraw the circuit one last time. voltage source of 12 volts, and here we have 16 ohms. Now, this is your Thevenin equivalent circuit. That is your Thevenin equivalent circuit, and it is the exact same result that we got using the other method right here. 12 volts, 16 ohms, 12 volts, 16 ohms. So, these are two methods in which you can find the Thevenin equivalent circuit. I find this one to be simpler and less time consuming, especially if you're comfortable with source transformations. The first method requires a little bit of remembering equations and knowing how to implement them, but whichever method you feel comfortable with is up to you. But these are two ways in which you can find the equivalent the Thevenin equivalent circuit for this problem right here. Okay, and that is all for today. Thank you so much for watching, and I hope that was helpful.